A ball is suspended by a thread of length L at the point O on the wall, forming a small angle alpha with the vertical. The thread with the ball was deviated through a small angle beta and set free. Assuming the collision of the ball against the wall to be perfectly elastic, find the oscillation period of such a pendulum. So what's happening is that this ball is attached to a pivot point with a string, and ideally it wants to cover this full range of motion and go back. But it's being stopped by the wall, so its motion is cut short, and instead of covering this full path of its motion, instead it covers only part of it, and then goes back. And then it continues to oscillate like that. So what can we first do is find what the oscillation period would have been ideally if the motion was not cut short. So we can quickly derive what that oscillation period for a pendulum is. So the restoring force is mg, because this is what's causing its motion, the ball's motion. And this angle is also beta. So if we write out the sum of forces equal to mass times acceleration, we only have this horizontal force in the x direction, which would be mg sine beta, equal to m acceleration. So m cancels out, and we get acceleration plus g sine beta equals 0. Okay, but beta, we said, was a small angle. So for small angles, beta is equal to sine beta, which is equal to tangent beta. And tangent beta would be opposite over adjacent, x over L. And x is just represents the displacement of our ball, or the position of our ball at any time. So we can now replace the sine beta with x over L. And now this equation follows our harmonic motion equation, where this is our omega squared. So our angular frequency is root g over L. Now if we want to convert that to a period, time period, t is 2 pi over omega, which is 2 pi root L over g. So this is the ideal oscillation period if there was no wall present. But remember that our problem is the wall, so it doesn't actually cover this motion because we have the wall that's stopping it. So let's actually just draw this extra segment that would have been there if there was no wall. And let's call this angle theta. Right? So this is the part of our motion that's missing because of the wall. So now we need to figure out what portion of the ideal motion is our ball actually following. So the actual period is going to be some fraction of the ideal time period. And for that, we're just going to make a diagram that represents the cyclical nature of our motion. So if we start over here and we cover the full cycle, right, we go all the way to the point that's actually not there and then return back, that makes a full circle, which is the ideal time period. It would follow this motion. But we don't actually cover that, right, because our motion gets stopped by the wall. We go here and then back. So our ball follows here, then this section represents the part that doesn't actually happen, and then we return back. And then we also know that because of our small angle approximations, this arc length will be beta L. Why do we know that? Because this would technically be L sine beta, but beta is very small. So L sine beta is the same thing as beta. So this is sine L beta, and this is L alpha. So our maximum amplitude is L beta, right? Because this is the arc length that we cover through half of the motion. So half of the motion covers L beta. But then after we reach this point, the next section of our motion, we only cover L alpha, which is represented right here. And this is cutting our diameter, or cutting our radius a little bit short. And now because this is a radius, that means that this length is the same as this length, because they're both radii. So now we can find what how alpha relates to beta. So using this little triangle, we know that cosine alpha or cosine theta equals adjacent over hypotenuse. And L can cancel out. So theta equals inverse cosine of alpha over beta. Now if we return back to our previous statement, using this circle diagram, we can tell that the portion of the entire motion that our actual motion has is just going to be 2 pi minus 2 theta. So 2 pi minus 2 theta out of the entire motion, which is 2 pi. And now, knowing what T ideal is and knowing what theta is, we can simplify that. So we can simplify that right here. So the 2 can cancel out everywhere, so we get pi minus theta over pi times, and then T ideal is 2 pi root L over G. So pi cancels out. So if we simplify, we get 2 root L over G. And then in parentheses, we have pi minus theta, which is inverse cosine. Now we also have this identity that inverse cosine equals pi over 2 minus inverse sine. Let's just say of x. And we have negative cosine, so that means that negative cosine is minus pi over 2 plus sine. So let's simplify. So 2 root L over G, pi minus pi over 2 plus sine. And pi minus pi over 2 is just pi over 2. So we can replace that.